Swayam Prabha. Digital India. Educated India.
So, welcome back to lectures on advanced calculus for engineers, and this is lecture number 7 on evaluation of limits. So, in the previous lecture we have already seen how the limit is defined, and in particular this epsilon delta approach was also reviewed. So, in this lecture we will mainly focus on the evaluation of the limit and some, or in fact many worked problems where we will see the different situations to get the limit. So, in the previous lecture we have seen that this f x y as x y goes to 0 comma 0 is L if for a given real number epsilon we can find a real number delta such that this difference is less than epsilon whenever this x is from delta neighborhood of this x naught y naught point, the delta neighborhood of this x naught y naught point. And this approach is very useful for verifying that the given number is the limit, but not actually calculating the limit L. So, here we will mainly focus on that how to evaluate the limit of a function of two variables. So, there are some rules which I will just quickly review about the working with the limits, as we remember from the one variable case as well. So, for instance, we have the limit f x y as x y goes to x naught y naught is L 1, and then there is another function g x y goes to x naught y naught is L 2. In that case, if we want to find like k into f x y, so k will be just multiplied to this limit L 1. If we sum or subtract the two functions f x y and this g x y and then get the limit, so their limit will be simply added or subtracted accordingly as per the sign there. If we have the product, so we have the product of the limits, and if we have this quotient f x over g x and f x goes to L 1 and this g x goes to L 2, and of course, if L 2 is not equal to 0, then this will be like L 1 divided by L 2. Further generalization, there are rules which work for the infinity situations as well, or they deal with the infinity cases. So, x y goes to x naught y naught f x y is suppose infinity, and the other limit g x y is also infinity. In that case also we conclude that the f x y g x y when x y goes to x naught y naught will be also infinity, and their sum will be also infinity, and if f x y goes to infinity, the other one goes to minus infinity, for instance. In that case, the limit the limit of the product will also go to minus infinity. If one limit goes to infinity, the other one is finite real number. In that case, when we add the two functions, so of course, because this was going to infinity, the result is going to be infinity again. If we have one infinity, other one L, which is positive, and if we have this product situation f into g, so this was, since this L was positive here and this is going to infinity, so this will also go to plus infinity. And if suppose this is negative here, this L is negative, so in that case this is going to be negative, because that number will make that product negative. Well, if one is infinity, g is L, In that case, when we do the product, this is going to be 0 because this g is L and here the denominator is approaching to infinity. So, we will get that limit to 0. Now, coming to the evaluation. So, those were just the extension or the generalization of the rules we have in single variable calculus as well. Now, coming back to the limit for functions of two variables. So, there are more challenges than we have in case of function of one variable. Remember, in the case of one variable, we used to check the two sided limit. So, the limit from the left hand side, limit from the right hand side, and if these two limits are equal, then we say that we have the limit. So, that was the process we used to have in the evaluation. We can compute the right hand side limit, we can compute the left hand side limit, and then if they match, we say okay, this is the limit of the function. So, only the two directions we need to check in case of one dimensional case, in case of one variable case. But now we have the situation where there is a point here, suppose this x naught y naught, and we want to approach to this point from the neighborhood points. Then there are infinitely many directions we can basically approach to this point. So, that is the difference and the challenges we will have in case of this two dimensional situation. So, there are infinitely many paths which can approach to this point. So, here this x y goes to x naught y naught in the two dimensional plane. There are infinite number of paths joining this x y point in the neighborhood to this x naught y naught point. Well, so since the limit, if exists, is unique, that we know already. So, if it exists, it has to be unique, there cannot be two different limits. So, the limit should be the same along all the paths, that is also clear. So, in that situation, the limit cannot be obtained by approaching the point along a particular path. In case of single variable calculus, we have only two paths. So, it is easy to check. You check from the left hand side, check from the right hand side, and if these two matches, then you say that this is the limit, because there is no other path which can take you to this point. But in this case, there are infinitely many paths which go to this x naught y naught. So, we cannot evaluate the limit by approaching the point P along a particular path and finding the limit of f x y. So, that is the difference as compared to a single variable calculus. But this the process of obtaining a limit along some particular path could be helpful if the limit is dependent on the path, or basically the limit does not exist. So, if the limit depends on a path, so we have chosen two different paths and we are getting two different limits, then at least we can claim that the limit does not exist, because that is enough. The two paths are enough if the limits are different along these two different paths. But if the limit is same, then we cannot say anything, we cannot conclude about anything, because we do not know, there might be some path, some very unusual different paths along which the limit is different of that function. So, we will go through several examples now to deal some situations which covers a larger scenario of the evaluation of the limit in case of two variables. So, this is the first simple example. If we have like sin inverse x plus 2y and tan inverse 3x plus 6y. So, this is a one type of situations which we can easily handle and we can evaluate the limit. So, what is special in this case, that we have here x plus 2y and here also basically we have x plus 2y. So, the dependency is not actually independent on x and y. So, the x plus 2y and here also in this argument x plus 2y. So, they vary with the same variation. So, here what we can do, that if we set this x plus 2y to t, then what will happen in this case, then this will be sine inverse t and this will be tan inverse t, and as xy goes to 0 0 we know that t also go to 0. So, instead of finding this limit as xy goes to 0 0 sine inverse x plus 2y and tan inverse 3x plus 6y, we can find the limit t goes to 0 tan inverse or sine inverse t and tan inverse 3t, and now we have dependency of one variable only. So, this case reduces to the simple case of limit of one variable calculus, and in this case we know the limit. So, t goes to 0 sine inverse. So, this is 0 0 by 0 case, and we know the L'Hopital rule which we can apply here now. So, this is the derivative of sine inverse is 1 over 1 minus t square, the derivative of tan inverse is 3 over 1 plus 9 t square, and as t goes to 0. So, this goes to 1 there and this goes to 3 here. So, the limit is just 1 by 3 in this case. So, this was a simple situation where by setting a combination of this x y if possible, because that may not be possible in many situations, this is possible only in some special cases like here. So, we can convert the given limit into one variable case, and we are already comfortable with finding the limit in one variable situation. Here the example which where tan inverse y over x and x y goes to 0 comma 1. So, tan inverse y over x and we are approaching to 0 comma 1. So, suppose this is the point 0 comma 1. So, what we do here, we approach from the left hand side and from the right hand side here along this x axis and see what are the limits, because first we can really see a few paths, and if the limits are different then we do not have to do anything, we will simply say the limit does not exist. The problem comes when along some standard given paths the limit is the same, and in that case we have to then prove that what is actually the limit. So, here y is equal to 1, we fix y is equal to 1 as I said here. So, we will be fixing y is equal to 1 and approach from the two sides as x approaches to 0, and in that case when x approaches to 0 from the left hand side. So, all the numbers are negative there. So, 1 over x tan inverse 1 over x when x approaches to 0. So, tan inverse this minus infinity, and that will be minus pi by 2. Similarly, when we approach from the positive side, so 1 over x when x approaches to 0, this will be infinity. So, tan inverse infinity, and that is actually pi by 2. So, by this simple consideration we have realized that along these two different paths the limits are minus pi by 2 and then pi by 2. So, there are two different limits along two different paths, and then we need not to do any further analysis, and we can conclude here that the limit does not exist for this function. Another example where we will compute this limit along y is equal to x and along y is equal to x square for this function and see what are these limits. So, first here y is equal to x. So, along y is equal to x means we will substitute this y is equal to x there. So, we have, if we take this y is equal to x, so we will have x cube over x 4 and x square, and then the limit x goes to 0, because y is equal to x is fixed now. So, x y goes to 0 0 means x goes to 0. So, here we will have x over x square plus 1, and then the limit x goes to 0. So, x goes to 0, this will go to 0. So, simply we have that limit 0. In the other case, when y is equal to x square, so you have x square, then again x square, and here we have x 4 and then we have again x 4 there, and the limit x goes to 0, because this y is equal to x square also approaches to 0. So, y is equal to x also approaches to 0, but y is equal to x square, that is a different path, but that also approaches to 0. So, we have chosen this path here, y is equal to x square, and in this case what we realize that limit x goes to 0, we have here x 4 and here we have 2 x 4. So, that limit is just half. Well, so along this y is equal to x square we have realized that this limit is half, whereas along y is equal to x, along the straight line, the limit was half, and along this parabolic path, the limit is half. So, what we can now conclude here, that limit for this function as x y goes to 0 0 does not exist. Well, another example where we have x y over x square plus y square, and x y goes to 0 0 we are looking at. So, in those situations when we see that here also we have 1 plus 1, the 2 power, and here also we have 2 power. So, kind of this homogeneous functions. In that case, this y is equal to mx, if we substitute, we will see that the limit depends on m, and there again we can conclude the limit does not exist. So, let us see what is happening in this case. If we set y is equal to mx, so we have x into mx, and then we have x square, and then we have m square x square. So, x square will get cancelled from all numerator and denominator. We have m over 1 plus m square, and that is the limit. So, there is no x anymore here. So, where x goes to 0 is just m over 1 plus m square. What does that mean? That the limit depends on m. So, if we change the angle, so we change the slope of the path approaching to the 0 comma 0, we are getting a different limit. So, in this case the limit we have seen is m over 1 plus m square, and it depends on the path, and hence the limit does not exist. That is the conclusion in this case also. For such functions where we have x square plus y square term in particular, we can also use this alternative approach, that is the changing to polar coordinate, which is very useful, as we will observe, we will see in many cases. So, change to the polar coordinate system from the Cartesian, we know the transformation that x is r cos theta and y is r sin theta, and since there was a term x square plus y square which becomes r square. So, the expression really become a simpler. So, here the limit x y goes to 0 0 x y over x square plus y square will be just cos theta sin theta. How? Because when we change this x y, so in the Cartesian case we were going here x y to 0 0, x comma y was going to 0 0, but in case of the polar coordinate corresponding to this x y goes to 0 0, we will have r goes to 0, because that is the distance is the r from the origin to that point. So, if we let that distance r to 0, that means itself that x y goes to 0 comma 0 without restricting anything on theta. If we restrict on theta, that means we are fixing the path. So, if we let r to 0 without fixing anything on theta, that means we are covering basically all infinitely many paths. So, that is another plus point of using this approach, the change to polar coordinates, because if by letting this r to 0, if we can see that there is no dependency on theta, as a result we will say that this actually is independent of path, and this is the limit. But unfortunately, in this case when we have this x is equal to r cos theta and y is equal to r sin theta, and then we have here r square, and this limit r to 0 we are trying to evaluate, what happens that this r gets cancelled, and as a result we got cos theta sin theta. So, this is the limit. So, now this limit for different values of theta, we are getting a different limit. So, here we conclude, since this limit depends on theta, on angle theta, it does not exist. So, here the polar coordinate is going to be very useful for calculating the limit as well as showing that the limit does not exist in either case. For instance, here we have x square y over x square plus y square, and in this case if we change the coordinate system from Cartesian to polar coordinate, what will happen? So, x is equal to r cos theta and y is equal to r sin theta if we take and substitute here. So, x square means r square, then cos square theta, and y is r sin theta, and then divided by we have r square, and then we will take the limit r goes to 0, which corresponds to x y goes to 0 0. So, in this case this r gets cancelled. So, we have limit r to 0, r into sin theta and cos square theta. So, here sin theta plus into cos square theta is something bounded, and we have r goes to 0. So, definitely this is going to 0. So, now this is what we will claim, that this is the limit. We do not have to check now further, because we have not fixed the path actually while evaluating this limit. This is coming independent of path, or in other words we have covered all the paths, because here we were letting r to 0 without fixing anything on theta. So, that means we have covered all the paths and the limit is 0. So, that is the advantage we are having here by converting to the polar coordinate, because here we can evaluate the limit. Well, so this limit is 0 and no dependency on theta, hence the limit for this function exists and the value is 0 in this case. Some important remarks. So, the changing to the polar coordinate, substituting this x is equal to r cos theta, y is equal to r sin theta, and investigating the limit of the resulting expression as r goes to 0 is often very useful, as we have seen in the previous example itself, that we are able to find out the limit by substituting this x r cos theta, y r sin theta. Like another example, if we have here x cube, so you put this r cube cos square theta, then r square, and again you will have r into this cos cube theta, and then this is bounded quantity and r goes to 0, we have the limit 0. So, the limit is 0, or in other situation we have observed that this will depend on theta and we can claim that the limit does not exist. So, this is helpful in both the cases, whether limit exists or limit does not exist. This is helpful in either case. But this changing to polar coordinate does not always help, or as we will see those situations that it does not always help, and sometimes this transformation may tempt us to false conclusions. So, we have to be little careful when we substitute or when we change to the polar coordinate, and when we pass to the limit as r goes to 0, we have to be careful. For instance, here x square y over x 4 plus y square, this example we have just seen before, the limit does not exist. But let us see what will happen if we change to the polar coordinate and let r to 0. So, we have r cube, then cos square theta sin theta, here r 4 and so on. After cancelling this r, we have r cos square theta and sin theta, then we have cos 4 theta r square and then sin square theta. So, what we may actually do the mistake here, that when r goes to 0, since r is sitting there, we may say okay, this is 0, but that is wrong, because there was the other expression also together here with this r, and we have to see whether we can show that this is a bounded one by some number, and in that case r goes to 0, we are free to we are allowed to say that this limit is 0. But here we do not know at this moment, because there is something in the denominator also. So, we need to be very careful when while evaluating this limit in such a situation where the expression sitting with r, for instance, is not bounded. So, if we fix theta, any theta we fix there is no problem. We can set that the limit is 0 because for a given theta something finite we do see here, and then one can conclude that this limit is 0. But otherwise without fixing the theta we cannot say about the existence of the limit. So, for instance, if we pick this path r sin theta is equal to r square cos square theta, which is corresponding to y is equal to x square, so that parabolic path. So, if we take that parabolic path, what will happen to this limit? We substitute there for r sin theta, in place of r sin theta we will put r square cos square theta. So, if we change that, earlier also we have seen in this particular case the value is half. So, the conclusion is we need to be very careful when we are evaluating this limit, because of unboundedness of the function which is sitting along with this r may lead to false conclusion. So, in the earlier case when we have seen that r something cos theta or sin theta was sitting. So, we know that this quantity is bounded, whatever theta you pick and then the limit r goes to 0, this will go to 0, but here that is not the situation. Well, so limit does not exist in that case. Now, to conclude here, we have gone through a very important section of this two variable calculus, that is the evaluation of limit, which is very useful, and the difference from the one dimensional case was that here now you have infinitely many paths approaching to a particular point, and in this case just fixing some path and evaluating limit can only help if those limits are different to conclude that the limit does not exist, but taking several paths and then we have a same limit, then we cannot conclude whether limit exists or limit does not exist. Another point was that this changing to polar coordinate is very useful for the evaluation of limit as well as for claiming that the limit does not exist. In either case, changing polar coordinate was very useful, and we need to be careful. That was another message we have seen in the previous example where limit does not exist actually, and we somehow conclude if we are not careful enough there, we may conclude that the limit exists. So, we need to be careful while evaluating that limit. So, these are the references we have used for preparing this lecture, and with this I thank you very much for your patience listening this lecture.